Last section in chapter 6 actually ties back to chapter 5, where we're using binomial probabilities, and here we're going to approximate these binomial probabilities with a normal model. There are two things that need to be true in order to use this method. So the first is that the sample meets the BINS requirement from the last chapter. Binomial, independent, number of trials is fixed, and the success probability is constant. Okay? If that's not true, we also can have a simple random sample of a given sample size with a fixed probability of success. The second requirement is that when we look at the number of successes and number of failures, what I mean by that is the n times p and n times q, we have to have values that are greater than or equal to 10 for both of those. If those requirements are satisfied, we can use a normal model to approximate our probabilities, and the mean is going to be n times p, standard deviation, radical, NPQ. One thing to keep in mind is that the binomial model is discrete. It's for countable data. That's not the case for the normal model. The normal model is continuous. We can find the probability for anything, whether it's 2, 3, or 2.75924. Okay, we adjust for this continuity correction by moving away from our value, 0.5 above, 0.5 below, to have a little slice of the normal model that's cut out. I'm going to show you what I mean in our first example. A survey from Viking River Cruises that included a request for an email address was sent out to 40,000 people. Assume that the percentage of responses with an email address is 3%. What's the normal approximation for this distribution? To start, let's go through those 4 criteria to identify this as binomial. It's binary. There are 2 outcomes. Either we get an email or we don't. Trials are independent. If someone gives their email address, it doesn't affect the probability that the next person is going to give their email address. We have a fixed number of trials, which is 40,000, and a constant probability of success, 3%. So that being the case, the mean of this distribution will be NP. We get 1,200. We expect to get 1,200 email addresses from this survey with a standard deviation of radical NPQ, which gives us 34.117. So the normal model would have those 2 parameters. Now I had mentioned cutting out a slice of this normal curve, and I'm going to show you what I mean here. We have this distribution centered at 1,200 with a standard deviation of 34.117. We're being asked what's the probability that we get exactly 1150. Now the issue is when we use z-scores, we can't find a probability of exactly that amount. If we look that up in the table, it's going to tell us what's the probability of getting a value to the left of it. Okay, so we can find the probability of getting at most 1150 or at least 1150, but we can't find the probability of getting exactly 1150 using the normal model. So we're going to cut out a little slice of this normal model. Okay, half a step to the left, half a step to the right. By half a step, I mean we're just going to subtract 0.5 from that 1150. We're at 1149.5. And then we're going to do the same thing on the right side, 1150 plus 0.5. And we want to find the probability that we end up in between these 2 dotted blue lines here. So we need z-scores for both of those dotted lines. Okay, subtract the mean, divide by the standard deviation for each of these values. Okay, we get negative 1.48 for the one on the left, negative 1.45 for the one on the right, and then we look both of those values up in our z-table. So this one is 0.0694, and this next one is 0.0735. Obviously, if we want to find in between those, we're just going to subtract those 2 numbers, and we get a 0.41% chance that we end up with exactly 1,150 email addresses. So with that being said, what's the probability that instead of getting exactly 1150, we get at least 1150? Now, since this is discrete data, we want to start off by figuring out whether or not we're going to include this section right here. Okay, now this is no longer relevant. Let's get rid of that. Okay, so does the word at least include 1150 or does it start above 1150? At least means we would want 1150 or more. We want to include that, which means we don't care about this rightmost dotted line. Okay, we're going to go to the left of 1149.5, so that little shaded red section is included in our probability. So we get rid of that shaded line to the right, and we want the probability of everything to the left of this dotted line. Okay, we picked the left one because we want to include the 1150. If it said, what's the probability that we got more than 1150 responses? Well, that wouldn't include 1150, so we would start at the line on the right of it. Now, we already did a z-score and a probability for that. We got 0.0694. Remember, that's the probability that we get something less than that. So we're going to do 1 minus, and we get our answer, 93.06%. Now, I know a lot of people get confused by the whole at least versus more than explanation. Here's a slide showing the key phrases that they'll use. Okay, so we have at least versus more than, and all of these have to do with a probability of 8. If it says at least 8, we want to include that 8. We have 8 and everything above it, which means since this data is actually discrete, it's countable, on the normal curve, we go a half a step to the left and we shade everything to the right of it. Compare that to more than 8. Okay, more than 8 doesn't include 8. Okay, we would start at 9 normally, but since we're on a continuous curve, we go right in between 8 and 9, and we start there at 8.5. Go everything higher than that. Okay, these two also always go together. At most 8 versus fewer than 8. At most includes 8 in that shaded area. Fewer does not include 8. Let's do another example. A new sales gimmick has 30% of M&Ms covered with speckles. These groovy candies are mixed randomly with the normal candies as they are put into the bags. At the production plant, a batch of 10,000 M&Ms has been mixed. We'll be choosing a sample of 55. Verify that the conditions are met. Now, normally we would check bins here, but the issue is that these are technically not independent and we don't really have a constant probability of success because when we choose an M&M, if we get a speckled one, that's changing the probability that the next one is speckled. Okay, because we have one less speckled one in the batch of 10,000. So I'm going to describe this differently. Trials are binary. We have a random sample of size 55 and a probability of success that's relatively constant. So in other words, the changes that we're seeing in terms of their independence and that probability of success are so negligible that we can ignore them. Typically, we can make that decision to ignore those differences as long as our sample size is less than 10% of the whole population. A standard bag of M&Ms includes 55. What's the mean and standard deviation for the number of groovy candies in a standard bag? Mean is n times p. We would expect to get 16.5. Obviously, we couldn't get 16.5, but averages are okay to be decimals. Standard deviation radical NPQ, 1.025. Verify that a normal model can be applied to this problem. Requirements are met for a binomial distribution, as we showed in part A. The other thing we check is, do we have at least 10 successes and failures? NP we already checked, we got 16.5. N times Q, this is the number of failures, the number of non-groovy candies, we get 38.5. These are both at least 10, so we can use a normal model. This is really just checking to see, do we have enough data to fill out the tails in a normal distribution? What's the probability that you receive more than 20 groovy M&Ms in a bag? We know we have a mean of 16.5, and we want to find the probability that we get more than 20. So again, we draw those two lines on each side because this is discrete data. We have a countable number of M&Ms, and we're finding its probability on a continuous curve. So that left dotted line is 19.5, the right one is 20.5. When it's asking us to find the probability that we get more than 20, do we want to include this middle section where 20 is, or do we not want to include it? More than 20 would not include it, which means we would start here and find everything to the right of it. Okay, so we only want the z-score for that 20.5. Okay, we can throw this one out. We get a z-score of 3.90. That's a really high z-score. It's off our table. It ends up being 0.9999 plus. Remember, that's the area this way. So the probability that we end up with more than 20 is essentially 0. Shortly after the promotion begins, company management receives an angry email from a customer saying that they purchased a bag of candy but didn't receive any speckled M&Ms. What are the chances of this occurring? We have our same curve centered at 16.5. What's the probability that they got 0 M&Ms? Again, on a normal curve, we can't find the probability that they got exactly 0. We can only find less than or more than it. So to find exactly 0, we want to move a half step to the right, half step to the left. So we're at negative 0.5, 0.5, and we're going to find the area in between these two dotted lines. Okay, so we need z-scores for both of them. The lower one, we get a z-score of negative 16.59. That's a really, really, really small z-score. So there's pretty much no area over here. We'll call it 0 plus. And then on the high side, we get another really, really, really low z-score, negative 15.61, which means it's just another 0 plus. So we would subtract these two to find the area in between them, and it's still 0 plus. Lastly, in an attempt to gain publicity, the company creates 5 bags that are filled entirely with groovy candies. Find one, and you win an all-expenses-paid trip to Hawaii. Some of the company is worried that the bags might mistakenly be filled with 55 speckled candies, and they'll have to give out extra trips to Hawaii. What are the chances of this happening? Let's do this one the old way with the binomial probability equation. Our sample size is 55, and we want all 55 to be chosen as speckled. So 55 is also the x. So we have 55, choose 55. There's a 0.3 chance that a M&M is speckled, and we want all 55 to be speckled. The 70% chance that is not speckled gets a 0 because we don't want any chosen that are not speckled. This gives us a probability of 1.74 times 10 to the negative 29th. It's very unreasonable to have this worry that these bags might mistakenly be filled with all groovy candies.